Okay, so question 3 is about proving that if you map the composition of two functions, it's the same as mapping G first and then mapping F afterwards. So this question is going to be a structural induction question where we prove a property for all lists. So we're going to do induction on lists. So state and prove the base case goal. Alright, so the base case goal is to prove this property here for XS replaced with the empty list. So we want to prove map F map G empty equals map F compose G empty. Now that's the property we want to prove, so let's prove it. Proof. The left-hand side is equal to all that stuff. Map F map G empty. By the definition of map any function onto the empty list is empty list. This becomes map F empty by M1, which becomes empty by M1. And the right hand side is map the function F compose G to the empty list. And then again, F compose G, whatever this is, this whole thing, it can be treated as like a single function because that's exactly what it is. It's a function that does G and then does F afterwards. So I can map this like any other function. I can just insert F compose G for F here and get empty by M1. Therefore, left-hand side equals right-hand side. Cool. Alright, next, state the inductive hypothesis. So the inductive hypothesis is that we're going to assume for all functions f and for all functions g, this property holds for a list xs. So our inductive hypothesis is assume for a list xs, for all f, for all g, map f map g xs equals map f compose g xs. You'll note that I've quantified f and g because they can be anything, but I haven't quantified xs. And the reason why that is because when you prove something using the inductive hypothesis, because we assume it's true for xs and prove it's true for x cons xs, the xs before has to be the same as the xs afterwards. So if I quantified this with xs, I've essentially assumed what I'm trying to prove, right? I've assumed the property I'm trying to prove. So we're going to assume for some list xs, this property here, and then prove it for that same list xs with an x tacked on front. Okay, that's the idea. And the reason why we do that is because if you look at the definition of list induction, it's for all xs, p of xs implies for all x, p of x cons xs. Due to the way this is set up, this xs here is the same xs as this xs here. Okay, so you be careful with your quantifiers. I already did that. What's the next thing? Here we go. State and prove the step case goal. Okay, so step case goal. Goal. We want to prove this property here. So we want to prove for all new elements x, for all f, for all g, map f map g xs equals map f compose g xs. You notice that xs is a free variable, and so where xs is the same as in the inductive hypothesis. It's not necessary to put this line here. This line here will be perfectly adequate. It's just, it's good practice to reference what the xs is. Okay, so let's do it. I'm going to let x, f, and g be arbitrary. And we'll start with the left-hand side, which is this rot. Map f, map g, xs. X cons. Oh, whoops! I've left in my x cons xs. Whoopsies. X cons xs x cons xs. There, that's better. So, for all new elements x and for all functions f and g, prove that mapping f and mapping g on this list is the same as mapping the composition over that list. So, my mistake. That's better. So, start with the left-hand side. Map g x cons xs. So you apply g to x and then apply map g to the rest of the list. So we'll do that. Just keep my rules here in view. Is that visible? Yep, there we go. So this is going to become map f map g applied to x cons onto map g xs. Cool, by rule M2. And so then we do map f, apply f to the first element and then map f on the rest. So g of x is an element, right? Just like any other. This is going to get us f of gx cons onto map f on what's left over. Map f, map g xs. Again by M2. F of g of x is the same as f compose g of x by rule C. So f dot g x is the same as this term here. Map f, map g, g xs by something by rule C. We can use our inductive hypothesis, which was here, to replace this term here, map two functions with map the composition. So we will do that. F dot g applied to x cons map f compose g onto xs by IH. I didn't label my inductive hypothesis, so I'll label it. There we go. And then we need to combine this back together. So we use the definition of map backwards to combine these two terms back together again. So then we're going to get map f compose g onto x cons xs by M2. And there we go. That's the proof.